Resonance. When you first tried using a swing unaided, you probably swung your legs wildly back and forth and got nowhere. Eventually you learned to gently move your legs back and forth in time with the swing, and the amplitude started to increase. You were providing a driving force at the natural frequency of the swing. You were also adding as much or more energy than was being lost through damping. Any oscillating system that experiences a driving force at its natural frequency will experience what is called resonance. The amplitude of the oscillations will increase until the system breaks, or until the energy lost through damping increases to match the energy input. You have probably experienced a panel on a bus vibrating noisily while the bus is stationary, but being far less violent as the bus speeds up. This occurs when the frequency of rotation of the engine equals the natural frequency of the panel. As the engine speed increases, the frequencies no longer match, and resonance stops. Buildings in earthquake zones are designed to have natural frequencies very different to those likely to be produced by the earthquake. One very dramatic case of resonance destroyed the Tacoma Narrows Bridge, which collapsed just 4 months after opening in 1940, or to a lesser extent occurring on the London Millennium Bridge, which was opened in 2000. An internet search will quickly find videos of both these events. This arrangement is designed to show resonance and is called Barton's pendulums. We have a heavy driver pendulum and several light paper cone pendulums of different lengths. These two, the driver and this pendulum, have the same length from the top here. Pendulum with the same length as the driver, and therefore the same natural frequency, will show a large amplitude due to resonance. All the pendulums will oscillate at the frequency of the driver, with the resonating pendulum a quarter of a time period behind the driver. We can now see two short videos of Barton's pendulums in motion. Resonance and damping. If we apply damping to a forced oscillator, we see the following behaviour. Here we have a graph of the amplitude of forced vibration, for instance that of one of the paper cones on the Barton's pendulums, against the frequency of the driver. With no damping, we get something like this. So this is an undamped system, where at the natural frequency of the forced oscillator we get a sharp peak of increased amplitude. With light damping, we get behaviour something like this. And with heavier damping, behaviour like this. So we see as the level of damping increases, the amplitude of the resonating oscillator reduces from this to this to this amplitude, but it is apparent over a wider frequency range. Also with heavy damping, the peak amplitude occurs at less than the natural frequency. See here the peak is at the natural frequency, and here it's gone across to the left, and here further across to the left. So here we have the heavy driver pendulum and the light paper cone pendulums of different lengths. This one having the same length as the driver. You'll see when I run the video, this pendulum has a much greater amplitude of swing than the others. You'll also notice that all the pendulums swing with the same frequency as the driver. The resonating pendulum is a quarter of a time period behind the driver. Here we have an end view showing the amplitude and frequencies of the pendulums more clearly. Uses of resonance. We've looked at some problems with resonance, but resonance can be useful. The MRI, or magnetic resonance imaging scanner, uses the resonance of nuclei to create an image. When you tune in a radio, you're making it resonate with the transmission frequency of the desired radio station. And microwave ovens make the water molecules in your food resonate. This heats up the surrounding molecules.